an exciting day in your chemistry career because you get to meet kind of the well-known, at least in the world of chemistry, ideal gas law, also known as PV equals nRT. And so in reality, kind of the three different gas laws, Boyle's, Charles, and Gay-Lussac's that we learned about yesterday, all kind of stem from this larger, kind of more comprehensive law that's called the ideal gas law. And so it's designed to kind of not only show the relationship between pressure, volume, and temperature, but what makes it special is it also includes this little n right here, which tells you the amount of gas in the number of moles, okay? And so you should recognize kind of the variables pressure, P, volume, V, and temperature, T. And so N, again, is amount based in moles. And then we also have kind of a new variable here that's a big R. This is referred to as the gas constant, and it has a set value of 0.082057. And it has pretty complicated units to account for all the variables. It's a liter times an atmosphere over a Kelvin times a mole. And so it incorporates and relates kind of the pressure, volume, temperature, and moles kind of all in one. All right. And so basically on this, we're going to jump kind of straight into the calculations. You know, if you end up taking college chem, you'll probably go a little more in depth on the theory behind the ideal gas law on how the ideal gas law works. But for our purposes, we're just going to kind of expose you to it and get you familiar with some of the calculations and then let you practice. All right, so our first problem here says a restaurant has a neon sign. There are 0.431 moles of neon gas inside the sign that occupy a volume of 1.52 liters. The temperature in the restaurant is 22 degrees Celsius. What is the pressure of the gas? All right. So first, let's kind of go ahead and list out our variables. Pressure, volume, the amount and the number of moles, the R value, and then the temperature. And you'll notice what makes this different than the combined gas law, which kind of incorporates Boyle's, Charles, Gay-Lussac's, is none of these variables are changing throughout the problem. If you remember, in the combined gas law, we would start with one set of conditions, and then we would change them and end up with a second set of conditions. So the way you know when to use the ideal gas law is, one, it should talk about amount, somehow in moles, or you're only given kind of one set of variables that's not changing. All right, so we're just looking at kind of a set state of the gas. All right, okay, so the pressure is what they tell us we're looking for. They tell us our volume is 0.43, not our volume. They tell us our number of moles is 0.431 moles. They tell us our volume is 1.52 liters. The R value is a set value that we just get kind of from the back of our textbook. And eventually, if you do enough of these problems, it kind of memorizes itself. 0.082057 liters times atmospheres over a Kelvin mole. And then finally, our temperature is 22.2 degrees Celsius. And again, just like the other gas laws, you'll want to go ahead and convert that temperature from Celsius to Kelvin by adding 273.15. And if you pull out your calculator, let's see what that gives you. 22.2. That's giving us 295.35 Kelvin. And kind of the reason now that the gas laws always have to have their temperature in Kelvin is actually due to the R value. All of the gas laws are kind of based off of this ideal gas equation. And since the R value is defined in terms of Kelvin, we need our temperatures defined in terms of Kelvin as well. All right. And so now we're ready to go ahead and solve. We've got PV equals nRT. And you'll sometimes hear people call this PIVNERT. So if you hear that, That's what they're talking about. Kind of a funny name. All right, so we're looking for pressure. We know the volume is 1.52. We'll set that equal to the moles of 0.431 times our R value of 0.082057, and then times our temperature of 295.35 Kelvin. Then just like before, to get P by itself, we'll divide both sides by 1.52. Okay, now let's get our calculator and do some math. So we'll take 0.431 times 0.082057 times 295.35, and then we'll divide all of that by 1.52. All right, and for our pressure, looks like our lowest number of sig figs is 3 sig figs. So our pressure we're getting is 6.87. Now you might ask, okay, well, there are a few different units for pressure. There's atmospheres, there's millimeters of mercury, which is it here? Well, whatever units are given in your R value will determine what units come out for the individual variables. So since the R value is defined in terms of atmospheres, our pressure is going to come out in terms of atmospheres. So the pressure of this gas is 6.87 atmospheres. All right. Let's go try a second problem. It's kind of got two parts. Okie doke. So this one says a sample of oxygen gas at 25 degrees Celsius has a volume of 11 liters and exerts a pressure of 660 millimeters of mercury. How many moles of gas are in the sample? All right, so let's start with the same process and list out our variables: pressure, volume, number of moles, the R value, and the temperature. Then we'll go through and fill in what we know. They tell us the pressure is 660 millimeters of mercury. They tell us the volume is 11 liters. We're looking for the number of moles. The R value is a set value of 0.082057, and that's liters per atmosphere over a Kelvin mole, or liters times atmosphere per Kelvin times mole. And then finally, our temperature is 25 degrees Celsius, which we'll go ahead and convert to Kelvin. That way those units will match the R value, which is also called the ideal gas constant. So 25 plus 273.15, that gives us 298.15 Kelvin. Now, just like it's important that the units of temperature match the gas constant, it's also important that the other variables match as well. So for example, your volume needs to be in liters, and your pressure also needs to be in atmospheres. But if you notice, our pressure is in millimeters of mercury at the moment. And so what we need to do is do kind of a quick conversion to take us from millimeters of mercury to atmospheres. And so if we look, we've got some pressure conversion factors here. And we're told that 1 atmosphere is equal to 760 millimeters of mercury. The other units that you see are just kind of other pressure units that you may get. There's torr, there's Pascal, and so pressure can be kind of measured in lots of different things depending on, kind of the field of study, whether it's, weather or engineering, physics, kind of lots of different stuff like that. And so what we're going to do, we're going to set up a quick conversion. We'll put millimeters of mercury in the bottom, atmospheres in the top, and we'll fill in our conversion factor. We know that 1 atmosphere is equal to 760 millimeters of mercury. Then we'll be dividing. So we'll take 660 divided by 760, gets us 0.8684 atmospheres for our pressure. So now that we've gotten all of our units in the correct place that they need to be, we're now ready to go ahead and plug in to the ideal gas equation, PV equals nRT, and this time we'll be solving for N, which is the amount in moles. So our pressure is 0.8684 times the volume, 11 liters, is equal to N, unknown, times R, 0.082057, times our temperature in Kelvin, which is 298.15. All right. So now, again, if we want M by itself, we need to do the opposite. Since we're multiplying by R and T, we'll divide both sides by those values to get M by itself and allow us to solve. Okay, so we'll go ahead and do that. Some long numbers to write out, but that's okay. All right, so now get that lovely calculator ready. And just be careful. Make sure that you have everything on top multiplied, divided by kind of everything on bottom multiplied. So we'll have 0.8684 times 11. Then hit your divided by key and open up a parentheses and do 0.082057 times 298.15. And again, make sure your calculator comes out with the right answer of 0.390 moles. And in this case, this gas is oxygen, so it's specifically moles of oxygen. All right, so now we know how much gas we have in this scenario. So last, it asks us, okay, how many grams of gas were present? And so this idea is that we'll be able to take the moles and using the molar mass, convert that to grams, just like we've been accustomed to doing kind of the whole semester. So we'll set up a conversion factor where we can go from moles of oxygen to grams of oxygen. We'll go to our periodic table and see that oxygen has a molar mass of 16. However, there are 2 oxygen atoms, so we'll do 16 times 2, which is 32 grams, and the molar mass is always recorded per 1 mole. So we'll start and do 0.390 times 32. That gets us 12.5 grams of oxygen. All right, and there we go. And so just a tip for you, sometimes in the practice problems, instead of asking you for how many moles of gas are in the sample, they may just start out by directly asking you how many grams are in the sample. And so you kind of have to remember, okay, grams doesn't appear directly in the PV equals nRT formula, but you have a connection that you can get to by solving for moles. So if you're ever asked for grams, go ahead and solve for moles first, then do what we did at the end and use the molar mass to convert to grams. Or, for example, if they tell you the number of grams, then what you can do is convert from grams to moles and then plug in the moles for the variable N within the equation. All right, so thanks for watching. Again, good luck as you practice, and definitely let me know if I can be of help to you in any way.